Thanks again, everybody, for joining us today. Right now, we have a session by 3 Google speakers, Brendan, Mehryar, and Francoise. All are leading various efforts at Google. Brendan is leading some of the research efforts on federated learning. Mehryar is leading a lot of research efforts on learning theory in general and applications to federated learning, privacy, and others. Francoise is leading a federated assisting team. So we're going to start with Brendan for now. Brendan, you can take over.
Thanks for the introduction, Peter, and thanks to everybody for being here. There's been a lot of really exciting work on federated learning happening at Google, both on the research side and on the deployment side. And so hopefully the 3 of us in this talk will be able to give you a little bit of an overview of some of the things that have been happening. But I just put a selection of recent paper titles from Google up here from the past 6 or 9 months. And as you can see, there's far too many of them to cover anything in any detail or even touch on all of them. But I think you'll hear at least a little bit about the bolded titles in this talk. And if you're interested in the other topics, please do check this work out. It's a lot of really good stuff. The first thing I want to start with is talking a little bit about privacy and federated learning. And this is actually really thinking that grew out of the workshop last year and the advances in open problems in federated learning paper that many of you all helped co-author. And Adam's question from yesterday really queued up this part of the talk nicely. There is definitely a real danger in the mental shortcut of just kind of saying FL equals privacy, right? And people do naturally want to take that shortcut. I think in at least my team's communication and most of the communication from Google, we've tried to be very careful about this. If we are not doing a good job, please feel free to call us out privately first if you can, but we want to get this right. And so I think the goal of this talk, think about this not as so much as me talking to you about something you don't know. That is certainly not the case with this audience. This is really me trying to give our best effort at kind of presenting some of the nuances of privacy and federated learning, and then looking for feedback from everybody in the audience here. This is something we want to continue to refine as we figure out the best ways to talk about these complicated topics. And I think the place to start is first acknowledging that if you're going to talk about privacy and federated learning, that's more than just privacy for the training of a single model, the federated training part of things. There's a model engineer in the loop. They're developing that model, doing hyperparameter tuning, model architecture searches, and so on, looking at metrics. It's an iterative human-in-the-loop process. And then finally, there's usually a model deployment stage of that at the end. And all aspects of this full FL workflow have privacy considerations that need to be made. So the way we've started trying to talk about this is by asking the question, what private information might an actor learn with access to different parts of the full FL system? For example, what can you learn potentially with physical access to the device, or access to the byte sent over the network, or even root access to the coordinating server? And then, of course, what could you learn with access to the models and metrics that we release to the model engineer that they need to do their job? And finally, what could you learn with access to the final model that we deploy, say, to all Android devices? So you can see immediately that privacy isn't, certainly not a binary quantity. It's not something you either have or don't have, but it's not even really a scalar quantity, and that you can look at privacy kind of independently for all of these different threat models. And then I think the place to start is by saying, first of all, FL doesn't solve all of these potential privacy problems, but FL is guided by a number of privacy principles that do have clear advantages. So there's the principle of minimizing data exposure, keeping raw data on device and only doing focus collection. So sending updates that are as focused as we can get to the particular task at hand, say model training or model evaluation. Those updates are anonymous and ephemeral. We discard them as soon as we can. We aggregate as soon as we can. So in general, we're trying to push any processing that removes information from data that we might not need as early as possible in the pipeline. And so that comes in as say, only an aggregate release. We're never going to release any individual user data. We're only going to release things that are suitable aggregates. But you know, even with all of those nice privacy principles that are baked into FL, there are many other complementary technologies that we might want to deploy here. So for access to the device and the network, of course, encryption at rest and on the wire is kind of table stakes. For access at the server or on the network potentially, one access is local differential privacy, which kind of presumes the actor is going to get access to the unencrypted update from a single client, and then adds noise in order to ensure that they can't learn too much from that user's update. But one thing that's interesting is for individual users' updates, there's nothing in FL that really requires anybody to have access to them. They're not what we want. What we want are the aggregates. And so there's interesting technologies like secure enclaves, general purpose secure multi-party computation, or specializations of MPC like secure aggregation that can go even farther than local DP does and say, hey, we're going to try to, by technological means, make it impossible for an actor to see the individual user update. And then the considerations with the released models and metrics and the final deployed models are a little bit different. We can't just completely hide those using security or crypto techniques. The model engineer and the device need to have access to those in order for things to work. So here's where we have to walk a more nuanced kind of utility versus privacy trade-off. And central or distributed differential privacy is a really powerful tool that lets us say we're still going to learn the aggregate information that is valuable without memorizing any one user's data. But a very, differential privacy usually comes in the form of epsilon delta guarantees, formal proofs. Unfortunately, kind of a proof statement doesn't protect you from bugs in your math, bugs in the proof itself, and of course those have happened, or bugs in your system if it doesn't faithfully implement the algorithm that you are claiming to implement. And finally, the DP guarantees can be very conservative, and that the actual privacy protection you're getting is much stronger than we currently know how to prove. So for all of those reasons, I think we're increasingly seeing that various forms of empirical privacy auditing are a very important part of the picture of protecting things like released models and metrics. So that's kind of the broad framing of privacy as we're thinking about it currently, how different technologies fit in and the different notions of protection that we'd like to get. As I said, feedback is very much welcome. Now I want to dive in a little bit and say that despite those caveats that go along with having a formal epsilon delta guarantee, that is kind of the gold standard we'd like to shoot for. But there's some additional challenges we've realized for getting precise differential privacy guarantees in real-world cross-device FL scenarios that I think pose a really interesting set of open questions. The challenges here are that there is no fixed or known population size to say sample from or shuffle to take direct advantage of existing amplification techniques. Client availability, the availability of devices to participate is kind of a complex dynamical system due to multiple system layers and local participation constraints, opt-ins and so on. So it's hard to know. It's not like central DP where you have the whole data set there and you can do whatever you want with it. Even if we're trying to get a central DP guarantee, because of the privacy principles of FL, our hands are a little bit tied in how we can even understand the data set we're working with. And of course, there's also the issue that even if a client starts participating, it could drop out at any point of the protocol. So we need to account for all of these things. And I think one good way to do that is to model the environment of FL, the environment that the DP mechanism is running in, as a adversarial process, so nature that is possibly malicious and adaptive, which raises the bar substantially in terms of the types of analysis you need. So given that setting, what kind of mechanisms do we want? Well, of course, we want good privacy versus utility trade-offs, but that's not enough. We really want to be robust to nature's choices about client availability and client dropout. And what I mean by that is that, but we want both privacy and utility to be preserved, possibly at the expense of forward progress, right? Say due to who knows what, on a particular round of computation, you only had 10 clients check in where you were hoping to get updates from 1,000 clients. Well, you could add those 10 clients updates with a lot of noise, enough to guarantee privacy, but that noise might then destroy the utility of your model. It might kind of cause divergence. So we don't want that. You could also add the update from those 10 users with a small amount of noise and preserve utility, but that would destroy privacy. And we really don't want to do either of these things. We need a mechanism that kind of automatically adapts and is robust to this scenario and says, 10 clients isn't enough. We're either going to wait for more or abort this round and so on. So that's a different constraint than comes up in typical DP mechanisms. Another property we really need that is a byproduct of not having full access to kind of the database or the data set is we really want to develop mechanisms that are self-accounting, and that the server can compute that precise epsilon delta DP guarantee using the only information it has available through the protocol. If we have to introduce a bunch of other logging or send a bunch of additional information to the server in order to, know what epsilon DP guarantee we're getting, then that's not going to be great. So if you're interested in this topic, I can, for now, point you at some of our initial progress in this direction. We recently put this paper, Privacy Amplification via Random Check-ins, up on arXiv, and there's a recorded talk from Ohm on the workshop website that I would highly recommend. Another thing that we heard a fair bit about in Virginia's talk this morning and elsewhere in this workshop is the challenges of optimization in the federated setting, particularly in the face of heterogeneous data. So in the last couple of minutes I have here, I want to give a quick shout out to this recent work on adaptive federated optimization from a bunch of collaborators across teams here at Google. So we introduce a new family of algorithms using adaptive server-side update rules. There's some very nice theory that goes along with this that I won't have time to go into. The two things I did want to briefly emphasize are that we did a really extensive empirical evaluation of these algorithms, and all of this is available in open source via TensorFlow Federated. So I think this is a really nice set of benchmark problems. So some of you hopefully saw Zach's lightning talk introducing this work yesterday, so you can find the full talk on the website. But just briefly on the experiments, we have experiments on 6 data sets, or sorry, six different learning tasks, 6 different models across 4 data sets. All of those are easily available through TensorFlow Federated and can actually be used in any ML framework. The way we host that data and make it available is not TensorFlow specific. And the other thing that I think is really key for empirical work in federated learning, there's a lot of hyperparameters. So we took quite a bit of care in carefully tuning hyperparameters. And so that lets us provide some really strong baselines for these problems. Of course, all of this about optimization is really about training a single global model. And as we heard from Virginia this morning, I think, and particularly from Vitaly's talk yesterday, the obvious question, is a single global model really what we need? So this was perfectly queued up by Vitaly's talk yesterday. And I think that's a great segue to what Mehryar and some of what Francoise is going to talk about in the second 2 parts of this talk. So thank you very much, and I'll hand it over to Mehryar.
Thank you, Brendan, for the introduction. I'm Mehryar Mohri. I'm heading the learning theory team at Google. This is joint work with Yishai Mansour, who is a research scientist at Google and also a professor at Tel Aviv University. Jay Rowe, who's a software engineer in New York, and Ananthirtha Suresh, who is a research scientist at Google, also in New York, and who's also, by the way, the one who has made many of these slides. And so I want to thank him particularly, and also thank Brendan, Francoise Beaufrays, Rajiv Matthews, Shanshan, Kay, and many other colleagues who have helped with discussions about this topic. So let me start with the motivation for this work. Why do we need personalization? Consider the next word prediction problem on Gboard. If you start typing, I want to drink, the most likely completion could be tea for many people, say stereotypically in England or in India, but it would be perhaps wine for many French people, or, and people like maybe me and Francoise, for example. Therefore, one model does not fit all. Similar problems appear in speech recognition, image classification, and many other areas. Personalization is a key issue in federated learning. This is because, well, in general, a general view of federated learning is one, or a first one, is that of a centralized or a single model. In many cases, we can observe a significant gap in accuracy between a single or centralized model and a potential personalized one. So the main question then is, how can we learn a personalized model useful to users while benefiting from data from all clients? The learning scenario is as follows. There are millions or tens of millions of clients or users, but the label data for each client is very modest. It's in the order of 100. The total number of labeled samples, however, is quite large. It is in the order of billions. So the key question here is how to leverage that data to learn an accurate model for each client. This relates to some fundamental domain adaptation problems that I will discuss later. But let me first mention very quickly some related work, starting with work by Smith et al. On a multitask learning formulation of federated learning. The study of the connection between federated averaging, or FedAvg, and the first order model agnostic meta-learning MAML, or the use of MAML to design a better personalization or personalizable global model. The Aruba algorithm that was proposed somewhat recently by Kodak et al., which improves upon gradient-based method approaches. And a fine-tuning approach that essentially consists of starting with a global model and then tuning it on local data, although it is not clear if this approach benefits from any guarantee, however. So probably the most straightforward baseline to consider for this problem is simply to train a model on the labeled sample available for each user or each client. If we denote by D the complexity of the hypothesis set, which maybe it's VC dimension or pseudo dimension, the generalization bound for that method has the following form. It's going to depend on 1 over the square root of the local sample size. So typically, this type of guarantees would be vacuous for reasonably complex models. An alternative baseline is, of course, that of a centralized model trained on all the data. So in that case, while the size of the sample is very large, the issue is the mismatch between the distribution of training samples and that of a target user. In previous work, we have shown that a notion of discrepancy is a key measure of divergence between two distributions in adaptation. So here, the generalization bound has the following form. It depends on that discrepancy term, the last term, and on a more familiar term, which depends on 1 over square root of the global sample size. So here, that term is going to be fairly small, but however, there's a price to pay for that, and that is, again, the discrepancy term. So in picture, here's the difference between the local and global models. One is very prone to overfitting, that's the local one. And the other one suffers from that distribution mismatch, which formally we can characterize in terms of discrepancy. So can we find an alternative solution? One way to do so is to do clustering and to cluster users into domains and learn one model per domain, as shown on the figure. This helps increase the number of training samples for each domain. And one classical technique consists of using k-means clustering. Actually, in this case, you would have to extend it to using Bregman divergences, as it has been done in the past, since we are clustering actually distributions. Each user is, in fact, a distribution. So in that case, you have one centroid per cluster. Instead, here we are proposing a new clustering technique that we are referring to as being a hypothesis-based clustering. And that matches more closely the objective of personalization, which is that of having an accurate hypothesis per client, per domain here. This consists of finding Q clusters, as shown in the formula at the bottom of the slide, with one hypothesis per cluster with minimal loss. Obviously, in practice, we would be using an empirical version of that. We have also derived an efficient stochastic EM-type algorithm for this problem and derived generalization guarantees for this technique. So in picture, the guarantees for clustering are as follows. They are essentially somewhere in between the guarantee for the local model and that of the global model. In short, hypothesis-based clustering is an intermediate learning bound which benefits from the larger training sample on the average sample size for a cluster and a potentially smaller discrepancy between the two distributions, which you can expect to decrease as the number of clusters is decreasing. So an alternative solution for this problem is, and based on good theory, is a data interpolation technique instead. This is based on the assumption that a client distribution is an unknown mixture of the source distribution, which is a very natural assumption in a variety of cases, especially with a very large number of samples. The assumption is furthermore that therefore borrowing data from other clients can help improve learning guarantees and convergence. This is essentially the assumption that is adopted in some of the work in multiple source adaptation. In recent work, we have devised a new cover-based multiple source adaptation algorithm, which leverages the labeled sample points from the clients, and which benefits from favorable theoretical guarantees. And we have given two types of algorithms for this technique, one that is a model selection type algorithm, and another one that is a boosting type algorithm. Unfortunately, I won't have time to go to present those. But I do want to say that the running time, that running this algorithm separately for each client, as in the scenario of federated learning, will not be practical. So that's perhaps it's possible to further refine these solutions, but in the absence of that, we have been suggesting an alternative technique, which is an interpolation algorithm that we call Dapper. This consists of first training a global model, and then subsampling it, subsampling from the global data, and finally fine-tuning the global model on a mixture of the local and subsample data with the mixture weights chosen via cross-validation. So unlike fine-tune, this algorithm actually benefits from good theoretical guarantees. And furthermore, we have proven a theorem showing that for strongly convex losses, the convergence rate for this algorithm matches the desired guarantee, which is that of statistical guarantees, when subsampling is in the order of the size of the local data. The algorithm is efficient both in terms of its communication complexity and its computational time. So this is one of the second technique that I wanted to mention. Yet another alternative technique for this problem that is also very natural is an interpolation one between models. So we have proposed a new technique that we call Mapper. This is an efficient algorithm that finds the best local and global models jointly. Unlike some straightforward methods that learn these models independently, the algorithm benefits from favorable guarantees. In short, the bound depends on the size of the total sample, little m, which is very large in federated learning, and the complexity of the central model, B sub c, and the complexity of the local models, D sub L. P here is the number of clients. The communication cost is the same as training single models, but the inference model size here is relatively large. So let me quickly show some experimental results for these algorithms. These are results using the eMNIST dataset, which is a letter and digit recognition task with 3,400 users and 62 classes. Models were trained with the Federated agnostic loss, or this clustering, hypothesis clustering losses, and combined using either fine-tune, Dapper, or Mapper. In short, one interesting observation is that the hypothesis-based clustering already provides a substantial benefit of about 4 to 5% with just 2 clusters, and improves upon federated averaging and agnostic models. Dapper and Mapper further improve the accuracy by about 1%, but the eMNIST datasets are small, and the improvement over fine-tune are not significant. However, unlike fine-tune, Dapper and Mapper, as I mentioned, benefit from theoretical guarantees. I won't have time to discuss an alternative discrepancy minimization technique, but I can do that in response to questions. Let me finish up by mentioning that I briefly discussed three personalization techniques, and pointed out how they benefit from learning guarantees, hypothesis-based clustering, which is a new technique, Dapper, Mapper, data interpolation, model interpolation techniques. These are likely to be useful solutions in a variety of applications. But personalization remains a key area of research. I mentioned several related adaptation-based solutions with good theoretical basis. The challenge here is to see how these techniques, one of them that I mentioned, another one, that discrepancy minimization, how they can be leveraged efficiently in the context of federated learning. Another minor issue that comes up in personalization is that inherently the local labeled samples are small, and so very often the results are not statistically significantly different. That's it. I'll stop here.
Thanks. Maybe Francoise can take over.
You can hear me all right?
Yes.
All right. Do you want to go to the next slide? So what I will be talking about is first giving you a little recap. If you were at this workshop last year, you probably heard me talking about various things that we've done with federated learning in production. As a quick recap, my team has brought federated learning to a large-scale consumer product, which is Gboard, the Android Google keyboard. We launched in Gboard a bunch of models that have been learned with federated learning. One to do federated next word prediction in various languages, one that predicts emojis from the text that you're typing, And we've trained a bunch of different models. The main benefit, obviously, that we could give to our users by doing so is to reduce the amount of logging that we need to do on their data, which, of course, in the context of a keyboard is very private data. And the thing that is interesting is that because the models that were training for Gboard before we used federated learning were to a large extent a mix of different sources of proxy data, the fact that with federated learning we could go deeper into actual user data without compromising it brought significant quality improvements over the non-federated baseline. So it's essentially a win-win scenario where we can give more privacy and more quality in one shot. Next slide, please. So after launching a few models, we thought, okay, federated learning is very nice, but can we bring in differential privacy? And so we started training next word prediction models with differential privacy. As a reminder, these models are word level LSTM models with 10,000 outputs, 1.3 million parameters, so they're not huge models, right? And we started doing experiments in English with next word prediction, and you see here the difference in accuracy as a function of training between DP and a non-DP trained model. And you see that the two models are pretty close. So we could manage, now that didn't come for free, right? We had to do a lot of experiments, but eventually we could get to a point where, especially by increasing the number of clients per round, we could get to a point where we would get about the same quality. Yes, next slide, please. So now, these models were trained with differential privacy, but as Brandon said, there are a lot of assumptions on differential privacy when you apply it in an actual, production setup. So we weren't sure at all that any kind of epsilon delta that we could derive from these experiments were actually, something that was worth mentioning because of those assumptions. So we thought that the best thing to do were memorization studies, where we could follow the lead of this paper, The Secret Share, where secret strings are introduced in the training data in different ways, and then we can measure the propension of the model to memorize and to resurface those secrets. And Om presents some of these results in his talk. So with that, we could, sorry, back to the previous one. With that, we could verify that indeed the models that we're putting in production were very resistant to memorization. And in the process, we learned a few interesting things about memorization and federated averaging. Next slide, please. So from there, we moved into personalization, thinking that, again, these are very small models. Maybe we can bring more value to our users by offering personalization. Now, be aware that the Google keyboard, at least in its typing form, already has some mechanism to do personalization. It's very rudimentary from a technology viewpoint, but it is effective. So anything that we did here came on top of that. And was geared towards next word prediction. The benefits, obviously, of doing things on device are, again, privacy, but also when you think about personalization and production at scale, large systems take a lot of infrastructure that tend to be bulky and fragile. Doing things on device gives us a lot more robustness, and we're hoping that these algorithms will behave better for users in practice. Next slide, please. So we did some experiments in typing personalization for next word prediction, and we have implemented with Brandon's team a mechanism by which not only do we personalize the model on device, but we also check that this personalized model is actually better for the user on device than the baseline model would be. So there's kind of a gating mechanism. And what you can see here in this plot is the number of examples of devices where the accuracy would improve to the right with personalization or make things worse on the left. And you see there are very few devices or users for whom it would get worse, but those again are gated, and the model, if a regression is not presented to the user. However, we have a good portion of users for whom the gain is very real, and they will feel it when this is deployed on their device. Next slide, please. So after looking at typing personalization, we start looking at speech recognition. The Google keyboard has a functionality by which you can click and you can speak to your device and dictate your message. So here, what we're doing is using the voice input from the user and any kind of correction that they might do on their device. So let's say that they speak to someone and the name of that someone is not well understood by the speech recognition engine. The user will have an incentive to correct it by typing before sending that message to that person. And so we collect these signals and we can use them for supervision of the speech model. The signals are cached in a training cache where the training algorithm can run from, and then the trainer will convert the model into an inference model that can be presented to the user. Next slide, please. So before I tell you more about personalization, let me say something about the speech recognition model. This model runs on device, a sequence-to-sequence model following the architecture of an RNN transducer. It predicts word pieces, a few thousand of them. So the speech comes in, there's a feature extraction piece, and then there are two stacks of LSTM layers, the encoder and the decoder, that feed into a joint layer that mixes the information from both sources and makes prediction and has a recurrent path into the decoder. This model is about 80 times bigger than a keyboard typing model. So of course, personalizing it will be will be more tricky than personalizing a typing model. Next slide, please. So here I'm showing the distribution of parameters in the different components of the model. Since the speech model is so large, we decided that maybe there was a way by which we could personalize only a subset of the model. And so intuitively, what happens in the speech model is that the encoder portion is very much capturing the acoustics of the signal. The decoder is capturing more of the semantics, the words that you speak, and then the joint layer is mixing the two. The joint layer is very small. The encoder is the bulk of the model, and then the decoder is about 20% of it. Next slide, please. So with this, if you look at personalizing these different subnetworks and trying to get an intuition for how well they work, we did two experiments. The first one was using this R-trick speech, where obviously adapting to the acoustic characteristics of the voice is the most important portion. And when we tried to fine-tune in a personalized fashion the different components of the model, we noticed that indeed it is the encoder that matters the most. And we see a large decrease in word error rate by fine-tuning the encoder. Please click. Thank you. The second task was a task with non-desiratory speech, where we had a test set with a lot of foreign names that are hard for the recognizer to understand. So that's more of a language acquisition type of task. And here what we saw is that even though, again, training a larger portion of the model might be beneficial, it turns out that just tuning the joint layer, which is a very small fraction of the network, is sufficient to get a lot of the wins in terms of accuracy. And so we decided to zoom in on that scenario. Next slide, please. And if you think of fine-tuning and personalization from the point of view of the user, and you think about the scenario of acquiring complex names, often what the user would like to see is really one-shot learning. They would like it to be the case that when they speak a name, the speech recognition system doesn't get it right and they correct it once, the system can learn from that and doesn't require more examples. That is in practice hard to get right. Often it works, but there are many cases where it doesn't. And so we found that there are data augmentation techniques that can help a lot with achieving that one-shot learning goal. And so we did experiments where, in addition to fine-tuning to the actual user's data, we also create by text synthesis more strings, more waveforms that contain the names of the that the user wants to focus on. And we did that in different ways. We tried to synthesize the names by themselves. We tried to synthesize them within sentences in order to get some context. We tried to do it with a standard voice, but also with accented voice, because a lot of the speakers that we have in this data set are accented speakers. So we try to target that accent group, or even by doing multiple voices with multiple accents. And what the graph on the right shows you is that the recall of those names in the test set is increasing with the power of the data augmentation method that we're using. Next slide, please. So this is where we'll see if this works. Can you try to play? We'll see if you have permission.
My name is Keychain.
So what you see here is the recognition result.
My email address is keychain@google.com.
The result with personalization on the bottom screen and without on the top screen.
Play songs by Huang Shujun. Latest album by Liang Jingru. Where can I find the best pisang goreng in town? I like to eat roti canai. Hokkien noodle is my favorite. Can't talk right now.
So Keychain is the lead on this project. Next slide, please. The next one is a very short demo. There are two pieces. Oh, you may not be able to listen to this one. Anyway, I'll try to get broader access. But this is an example. Dimitri is a dysarthric person. Is a researcher, a mathematician actually, at Google, and he's from Russia. He became deaf at a very young age, so his voice is slightly difficult to understand for people who are not used to it. And here too, there are examples of his voice being learned by the personalization and rendering correctly. And that's it. Thank you.
Thanks thanks Francoise, and thanks for all three speakers. We're going to take questions right now. Let me switch the tab to Dory. Please post your questions on Dory. We're going to do a few minutes of questions. Let me put up Dory. I believe we have already a few questions, so let's see. Hopefully you can all see my screen. All right, so there's a question for Mehryar. Mehryar, you are with us, right?
I am here. I don't know if I can read the...
I'll read. All right, so Monica asks, could there be an advantage of using training dynamics, either different updates for each client over time, or during one local update, observe dynamics of parameters of clients to cluster them, or observe how fast they diverge from the global model instead of just using the final models?
I see. So yeah, I think that can be something interesting. I guess training dynamics is something that is rarely leveraged even in standard supervised learning. But in this setup, it could be actually very interesting to observe it. And some of the ideas like meta-learning actually are already somewhat close to kind of like looking at what happens as you change the model. Now, that being said, as you may have noticed, what I tried to do here was to emphasize quite a bit methods that benefit from good guarantees. And I guess, Monica, in this case, deriving good guarantees might be challenging, but still definitely worth looking at. Okay, another one.
Yeah, there's another question from Qiangliang. A great talk, Mehryar. I wonder, do you have any theoretical results for non-strongly convex or even non-convex objective functions? What is the challenge to carry out such analysis?
Okay, so it all depends on what kind of guarantees you wish to give, right? So for non-convex objective functions, so first of all, actually, this is an opportunity for me to, I think Brendan in his talk talked about optimization solutions based on some recent paper. Let me also take that opportunity to mention two sets of work of my team and people who are actually working with my team. One is an optimization algorithm that's known as Scaffold. And I think several of my co-authors are on this talk. This is work that was presented at ICML. And in that, actually, for example, Quan, we are showing how this algorithm benefits for guarantees both in the convex and non-convex cases. Okay. Now, the challenge of giving in general non-convex guarantees is both on the statistical and on the optimization side. What I just addressed was the optimization.
All right, thanks. So Krishna asks, this has great talk. Are the approaches you described privacy preserving?
Okay, that's a very good question. So quickly, very quickly, I want to say that the answer is yes to at least two of them. But it would be a long story to describe in detail some of the challenges. So Krishna, I invite you to look at our draft, our archive draft, in which we are describing in the appendix in detail, discussing some of these questions. But more work needs to be done for actually all of these personalization techniques from the privacy preserving point of view. Okay?
All right. Okay. I think we're going to continue having these discussions on Dory. Francoise, I think I now have access to the demo. Might be worth showing the demo real quick. Let me try to present. So let me play the first one.
You were insulted a co-founder of Access Israel.
So you see the system didn't understand Dimitri at all. The next slide is, the next demo is with personalization to his voice.
You were insulted a founder of Access Israel.
There we go. Thank you.
Thanks.
Thanks, Peter.
Yeah, thank you. All right, everyone. We're going to break for 5 minutes. So we're going to resume at 11:05, but we're going to be in 2 different rooms. So track 1 is going to be in this room. The other track is going to be, the security and privacy track is going to be in a different room. I just chatted the link to the other GVC. So please switch if you are attending or presenting in the second track, and we'll start in less than 5 minutes. Thank you.